Okay, so in question 12 here, we have a photograph on a person on a ladder which is propped against a wall at an angle theta to the horizontal. The ladder and the person form a system. The diagram shows 4 of the forces acting on the system. The friction between the wall and the ladder can be neglected. One of the forces has been labelled. The dot is the centre of gravity of the system. So that is the centre of gravity of the system. That's important. So this is the force acting at the centre of gravity. This is the weight of the system, the whole thing, weight of the whole system. This up here is a normal reaction of the ladder with the wall, and this is the normal reaction on the ladder from the floor. And we've got frictional forces on the floor of the ladder. Okay. B. Use the principle of moments to explain why the system is stable in the position shown, but will topple if theta becomes too large. So first of all, we want to explain what stable means. So stable means the system is in equilibrium. Now this means that there is 2 points. So we've got 2 things. We've got there is no resultant force. And that means all of the forces upwards. There's only one force upwards. Let me label this force R1, this one R2, this one W, and this one F, friction. There is no resultant force. So vertically, we would have R1 is equal to W, and horizontally, we would have, so just as we were just saying, vertically, R1 equals the weight, and horizontally, R2 is equal to F. That's one thing for equilibrium. And the other thing is, the second point is there is no resultant moment. So in other words, there is no resultant moment. The sum of the moments clockwise must equal sum of the moments anti-clockwise about the same point. Okay, so about the same point, the sum of the moments clockwise is the sum of the moments anti-clockwise. This is called the principle of moments. So remember, a moment is equal to a force times the perpendicular distance to a point. So now we've explained what it means to be in equilibrium. But let's look at this situation first, and we'll choose a point to take moments about. Taking moments about the bottom of the ladder. Why do I choose to take moments about the bottom of the ladder? It means the distance to these 2 forces is 0, so we can ignore these 2 forces. So we've only got that force and that force. So R2 causes a clockwise moment. And W causes an anti-clockwise moment. We just draw a little diagram to illustrate that a little bit. So I've got my ladder. I got two. Sorry, I seem to be having quite a lot of trouble with this particular question. We were just saying that moments about the bottom of the ladder, like this diagram here, R2 causes a clockwise moment and W causes an anti-clockwise moment, so it's in equilibrium. But as the angle increases, you see that the weight is now moved over to the right of the bottom of the ladder. So as theta increases, the W becomes a clockwise moment. So you've got R2 clockwise and W clockwise. So there is no anti-clockwise moments, so the ladder will topple, the ladder will turn over. Thank you.